So we've got air traffic controllers using radar to track aircraft. They've got a diagram here, shows a blip as it identifies an aircraft's indication. One aircraft A is 100 kilometers due east and 50 kilometers due north of a radar antenna bar. First, what is the distance from the radar antenna to the aircraft? So in that first question, you have a right angle triangle where you know this is 100 and this is 50. Did you remember the famous a squared plus b squared equals c squared formula? What do we have to remember about this formula? One of the letters is all by itself on one side. That's the c squared. That is always your hypotenuse. So in this situation, we would know what a and b are. Does it matter which one's a and which one's b? No. So we can have 100 squared plus 50 squared equals c squared. Obviously, this would be a calculator question, as those are some big numbers, and especially when you have to square root it. So we would do 100 squared plus 50 squared. And then to get c by itself, we would square root. Now, if this was non-calculator, you would do this. And if it was that, you would also have to reduce this as a mixed radical in lowest terms. Okay? Now, can you see, if I was doing this non-calculator, it's good practice from non-calculator stuff, can you see that this is the same as 100 times 125? And the square root of 100 is 10. So I might do that to help reduce it. And then, am I done? No. And it's okay that you do it in two different steps. Like this is 25 times 5. So this is 25 times 5. And square root of 25 is 5. So this reduces to 50 root 5. Of course, trigonometry is going to be a unit that you do lots of stuff with calculators. So if you had got 111.8, what units are we using? Kilometers. Kilometers. Right? That would be fine as well. Okay. Second question. Second question says, what is the angle between the tracking ray and due east? So we're asking for this angle theta. And I'm going to switch to green to do this question. Next thing from previous trigonometry. Did you ever learn this acronym? SOHCAHTOA. What did it stand for? This one told you that sine of any angle is always the ratio of the opposite over the hypotenuse. This one told you that cos of any angle is always the adjacent side divided by the hypotenuse. And this one told you that tangent of any angle is always the opposite side divided by the adjacent. SOHCAHTOA as a result. So in this situation, we want to find theta. And technically, we now know all three sides. We know this is 50, this is 100, and the side C is 111.8. But if I was solving for theta, I would like to use this one and this one. For one, this answer was rounded, so it's a little bit off. Secondly, I figured that one out. There is a chance I made a mistake while figuring something out. So it's better to use given information as opposed to using something you figured out, because if you made a mistake, then you're going to further make mistakes and get a wrong answer later on. So if I use those two sides and I want to find this angle, the hypotenuse is always the hypotenuse. But the opposite and the adjacent depend on which angle you're talking about. If I'm talking about the green angle theta, then the 50 is opposite and the 100 is adjacent. Then I would look at my SOHCAHTOA and I would say, The ratio that includes the opposite side and the adjacent side is tangent. So then I could write out the following. Tangent of theta is my opposite side, which was the 50, over my adjacent side, which is 100. And the beautiful thing about your calculator is that it has every single ratio memorized. It knows what angle gives us that. Now, in order for us to find that from the calculator, we have to tell the calculator we want to know the angle where the opposite over the adjacent is 50 over 100 for 10. We tell our calculator, I want to find theta by doing the inverse. Basically, same thing you do in lots of math. If you want to get just the theta by itself, you need to get rid of that tan in front. What's the opposite of something? It's an inverse. Okay? But a lot of the inverses we use have special names. Like, what's the opposite of squaring? Right? We say square rooting. We don't say squaring inverse. It could be. They could have named it that. Right? But for sine, cos, and tangent, when you want to get rid of the tangent, they have the inverse, and it's named that, tan inverse. That's not the only. There's another name for tan inverse. Does anyone know the other name for tan inverse? Not inverse tan.
Cotangent.
No, cotangent. Cotangent is the flip of tan. It's reciprocal. It's close. But you'll see a lot in older textbooks, instead of writing this, whoops, I'll keep it green. It's kind of fun. Arctan. There's arcsine and arccos. But I think tan inverse is really easy to remember. Plus, your calculators all have the tan with a little minus button instead of arctan. So we don't have to know this. But we go to our calculator now. Okay? And I've been doing my calculator right now is set in radians. You guys won't do radians until next semester. I'll go back to degrees. And now I can go second tan inverse of 50 divided by 100. And my calculator has it memorized. Exactly the only angle that will ever have 50 over 100. Okay? Oh, I love trigonometry. So much fun. 26.565. So we get our angle theta. Now there's another radar station in another spot. Yes. Are you in? So you are in radians. So you have to hit your right button and go from radians to click on degrees. Okay, there's another radar station. I'm going to call it R2. Seeing another aircraft, A2. This aircraft happens to be much closer than the previous one. It's only 2 kilometers this way and 1 kilometer this way. And we want to find this angle. Wow. Let's try that again. We want to find this angle. So we set everything up the same way. Okay? Sorry, I'm getting excited about this front. We set everything up the same way. It would be tan again, right? Tan of theta, opposite 1 over adjacent 2. And then you want to find theta, so you have to do tan inverse. 1 divided by 2. And you go to your calculator, and it has it memorized as well. And it memorized it to be 26.565 again. And this is the powerful thing about trigonometry. Okay? Mathematically, I hope you can see why they're the same. Mathematically, when I have 50 over 100, could I reduce that fraction? I could reduce that to 1/2. That's the same thing that happens here. Okay? Conceptually, though, this is a huge idea for trigonometry. If you make a small triangle, okay? Oh, I'm going to label that angle theta. Join those together. There we go. There's my small triangle. I am going to take that small triangle and hit this button 5 times. And wait, because nothing's happened. Ah, beautiful. I forgot that was do not touch this button today. Oh, there we go. What do you think? Right there? There. That was also a good button to push. All right, just the drama just increases. You so badly want to know what you're just itching to learn this big idea I'm going to show you. And now, take that same triangle. I draw it again, except this time, I made it bigger. Question. Would you agree that this side is now bigger than this side? It might have changed to 100. Would you agree that this side, if I made this 50 times bigger, this gets 50 times bigger? But the angle itself, when you make it bigger, yeah, the lines are fatter. And the lines being fatter give you the perception that this is a bigger angle than this one. But when triangles get extended bigger, and maybe it's easier to see if I would have just extended it that way. Now can you see that that angle in the corner of both the big triangle and the little one are identical? This is the power of trigonometry. They have found that no matter how big or how small you make the triangle, the ratios stay the same. So if I have this little triangle and the opposite over adjacent is a half, and this big triangle, the opposite over adjacent is half, that angle stays the same. And 26.565 will be what happens no matter how big or how small the triangle is. So I could do this. I could give you this is 26.565. And I could say this is 7. And you could tell me how long this side must be. What do you think? 3.5. And my calculator can tell me it's 3.5 because I could say that tan of 26.565 has to equal over 7. Whatever, that's my new variable, right? It's got turned a little bit. But the blue scribble over 7 has to be tan of 7. And if I want to get the blue scribble by itself, can you see I'd have to multiply both sides by 7. Check this out on my calculator. I say 7 times tan. That's not 10. 10 of this 26.565, all those decimal places. It says, oh, it has to be 3.5. This is the power of trigonometry. So because your calculator, mathematicians, have figured out every single angle possible, and what the opposite over adjacent is, opposite over hypotenuse, adjacent over hypotenuse. They're all built into your calculator. So if we have one angle and one side, and by the way, this works for SOHCAHTOA, only works for 90-degree angle triangles, then you can find the other sides. And now we can solve all sorts of math problems when we only know an angle. And if we only know the sides, we can find the angle. Okay. So now we have a general diagram in the construct the understanding. We can go straight down and make our 90-degree triangle, which would make this side x and this side y. Would you agree a squared plus b squared equals c squared? So we can write that x squared plus y squared equals r squared. That answers question number 1. That's writing r in terms of x and y. Technically, if you wanted to get r by itself, you could. You could square root And because we're dealing with a shape, is the side length of a triangle ever negative? No. So technically, R would just be the positive one. Question?
Wouldn't the root and the square should cancel? Like, wouldn't that just be x?
Ooh, that's a good question. Can I just make that x plus y? Order of operations here. Can I square root the individual ones, or do I have to do the adding first? So if you're ever wondering about that, take something that you know. Here's, you know the square root of 9? You guys, you know the square root of 16? So your question is this equal to 3 plus 4? Right? The answer is no, because why? If you added 9 and 16, you get 25. Close. And then if you square 25, you get 5. So it's interesting because our brain wants to do some math in situations where we're like, this is a confusing situation because I don't know what x is, I don't know what y is. Am I allowed to square root each of them and just make it x plus y? Doing it with numbers you know as a check is a great way to find out if you're doing math that you're allowed or math that you're not allowed. There are some times, okay, that you can do math that you're not allowed and accidentally get it wrong by doing a check. I'll give you a couple examples. Let's say I'm very bad at my times table. I don't know 3 times 5. I only know up to 2 times 2. And since I know that 2 times 2 is 4, the rule for multiplying must be you just add the numbers together. So this must equal 8. Brilliant. It works, doesn't it? 2 plus 2 is 4. So therefore, it must be okay. Doesn't work in this situation. So sometimes we can find wrong rules for math that work in certain situations. So we sometimes have to double check that it works in, if you like check a couple of numbers, okay, it didn't work here. It doesn't work in a couple of other ones. I'm pretty sure I can't do that now. Right? But sometimes you can find weird things that work. Oh, you want to see another weird one that works? All right. This one is awesome. Reduce to lowest terms. Okay? I like to just cancel out numbers. Okay? That's totally how you reduce. Isn't it? Is that allowed? No. But it's the right answer in this situation. But you're totally like, what? But if you try it in any other situation, it definitely, like 24 divided by 12, yeah, it definitely is equal to 4. No, it didn't work in that case. That one's supposed to be 2. But it worked in this situation. So we have all of these weird situations that work. And since we're doing trigonometry, I'll show you a weird one in trigonometry that works. We're going to do sine of x divided by n is equal to 6. And if you just cancel out the ends, it works. It's true. But obviously, not allowed. Okay. Sorry, we got off topic there. In a hurry. Great question. Next. The x-coordinate of P in terms of r and theta. So if I want to do the x-coordinate, that's my adjacent side, that's my opposite side, I can write, I don't like using red. That sine of theta would be, x-coordinate. That'll be cos of theta, because it's my adjacent side, is x over r. If I wanted to get x in terms of r and theta, that would be getting the x by itself. I would have to multiply both sides by r. That would be getting x by itself. And I could get the y-coordinate by itself because sine of theta is opposite over hypotenuse. And so the y-coordinate by itself would be r sine theta. I could do tan 2. Did I miss one before that? It's hidden under here. Is it probably the tan one? Yes. And tan of theta is opposite over adjacent. So if I wanted to get theta in terms of x and y by itself, theta by itself, I'd have to do tan inverse of y over x. So whenever it says in terms of, and this is going to be something that comes up quite a bit more, maybe in grade 12, this in terms of means you need to write an equation where the other side only has those variables. All right. So before we get to example 1, we are going to learn some preliminary definitions. Preliminary definition number 1 is what is an angle in standard position. I will highlight that whole thing. So mathematicians want to come up with a way so that if I tell you I have an angle of 35 degrees, you know how to draw it the same way I'm imagining it. And so we come up with this standard position of an angle. If I want to draw an angle in standard position of 35 degrees, I would draw my 4 quadrants from my x-axis and my y-axis. I would start from my positive x-axis and measure 35 degrees. Later, we're going to find out that negative angles also start at the positive x-axis. They just go in the clockwise direction. So an angle in standard position has to start from the positive x-axis. That's really important. So if someone's talking about an angle of 90 degrees in standard position, you would know it started here and went 90 degrees straight up and down. And that's going to be important because we're going to start thinking about solving trigonometry beyond just triangles in quadrant 1. We're also going to solve trigonometry if we don't have perfect SOHCAHTOA triangles. Not just 90 degrees, because you can draw a triangle without 90 degrees. And then you want to find those angles, right? If you draw a triangle, you're like, I want to solve this. That's kind of the exciting thing to do. So this is an angle in standard position, right? Anytime you find any other angle, and this is, oh my goodness, they're going to be like here. If I went this way, that is not an angle in standard position. In standard position, I would figure out this angle starting here to here. What would I guess that to be? Over 90? Maybe 110 degrees? 110 would be in standard position. The other angle would not be. In fact, we're going to learn, and we're going to call this angle a reference angle, which is going to be really important for solving things with trigonometry. Okay, so we now get to example number 1. Whew, that's too much information for you. Let's get rid of that. There we go. point 3, 4. 1, 2, 3, 1, 2, 3, 4. There's the point. 3, 4. It's in quadrant 1. Is on the terminal arm. So an angle in standard position starts on the positive x-axis, and we say that it ends at the terminal arm. Terminal is another word for end. So here's our angle in standard position, starting here, going this direction. And it goes through the point 3, 4. If you wanted to find out how long this side is, I'm going to draw a triangle. Straight down, straight across, makes a nice right angle. Can you see from this triangle? It's pretty easy to see this side is 3. And this side, 1, 2, 3, 4. This side is 4. And we can do a squared plus b squared equals c squared. Did you know that the a squared plus b squared equals c squared also only works if the angle is 90 degrees? We're going to have to get some new messed up formulas when the triangle's not 90 degrees. It's going to be fun. Yeah, don't look ahead. You don't know. Okay? Can't learn it before. Anyways, a squared plus b squared equals c squared. This is the most famous right-angled triangle. Do you recognize it? Some of you can do the mental math without it. This is 9 plus 16 is 25. Oh my goodness. It works out perfectly to be 5. The famous 3, 4, 5. And it's famous because it is used like carpentry, used a ton. You're building a house. Why are 90 degrees important for building houses? Right? You want your walls to be straight up and down. Right? It'd actually be kind of fun to build a house where all the walls were like different and be like, people would be like confused when they get in there. Certain pictures wouldn't hang right. Could be fun. There you go. Now some of you are now planning to build your own house and having it the most impractical that you can imagine. But carpenters will use that. They'll measure 3 feet out, 4 feet out. They'll measure their wall from those 2 points. If it's 5 feet, they're like, good. We're pretty much square. We're going straight up and down. This is important. Right? If you're completely off, it could throw off your whole house, and then that's going to be a problem. Okay? Off a little bit, they're not too concerned. As long as it's pretty close, we're going to be fine. Okay? Determine the primary trig ratios. What does this sentence or this mean? This is sine of theta, cos of theta, tan of theta. And when they're asking for the ratios, ratios are fractions, something over something. So if I want to write sine of theta, I would write what over what? Opposite over hypotenuse. Can you see that that would be the 4 is opposite? Here's the angle. 4 is the opposite, 5 is the hypotenuse. Cos, adjacent over hypotenuse, and tan would be opposite over adjacent. And again, your calculator has it memorized. It has it memorized for each of these. If I want to find theta, I could use any one of these. If I use the sine one, I want to get theta by itself. What's the opposite of sine? Sine inverse. So I go sine inverse of 4 over 5. And it tells me 53.13. But then someone says, no, I want to use this one. Well, the calculator says, well, let's see if I have it memorized. I'll do cos inverse of 3 over 5. 53.13. And if I did tan inverse, I would pause here for effect of drama, wondering what it could be, but you might already realize it's the same. It is the 53.130. So your calculator has that figured out, right? Could they do trigonometry before calculators? Yes. Oh my goodness.
Yeah, they had to figure it out somehow.
They had to figure it out somehow. So how did they do it? Well, ask your grandparents. Did they do trigonometry in high school? And did they have scientific calculators in high school? How did they do it? Okay? And the way that it works, let's see if I have one here. Oh, yes. Very good. There used to be, this one is a book of tables, originally done. Yeah, let's see a date in this one. It was extended. And he's stealing some tables from a table in Berlin in 1799 and another table in Paris from 1829. Just trying to see what the copyright of this book is. 1856. And what mathematicians would do is someone would like at the very beginning stages, someone would measure it out very precisely and get an accurate reading. Then they would develop mathematics to get it even more accurate. And they would produce books like this one. This book is 575 pages of just numbers. And like that's, ooh, this is where the plot thickens. No, it's just numbers throughout the whole thing. And here, you want sine of 2 degrees? It has sine of 2 degrees. How many decimal places do you want? You want 2.05 degrees? You would look on here, and then they have 7 digits of accuracy. So it used to be, if you wanted to figure out this question, you would have to go to your table and find 0.8 in your table somewhere. And then go across and you'd be like, oh, the angle that goes with 0.8 for sine is 53.130. And it used to be that grade 10 and grade 11 textbooks would have a simple table of these numbers at the back. Yes.
So the sine of that supposed to have a numerical value?
By itself, no. But as soon as you put an angle with it, like if I put sine, as soon as I put sine of, and I put that answer in, 53.130, it has an answer. It's exactly 0.8.
Why does that have an answer by itself?
Because 0.8 is what 4 divided by 5 is.
I know why did sine have an answer?
Sine itself is a function. So what a function is like, what number does square root have? It's like it doesn't have any number unless you put something inside of it, right? Square root of 16 is 4. But like, oh yeah, well what's square root? And then you're like, well, you need something in there in order to have it have a value. Same thing, sine by itself means nothing unless it has an angle. And once that angle is in there, it says, if you drew a right angle triangle, like pick an angle, 20 degrees, okay? So if I said, what's sine of 20? Well, if you had a protractor and measured 20 degrees, oh, I was close. That's about 20 degrees. It's very accurately drawn. Okay? Then I took out a ruler. and I measured. This is 16, that's about 17 inches. That's about 8 point, I don't know, 8.5. This is me being not very accurate. And this side, that's, I'll use tangent because same idea. Sine doesn't mean anything, but in my calculator, tangent of 20 comes out to a certain number. I can type that in. It tells me that I'm not very good at measuring, probably. But tangent of 20 tells me 0.3639. And this is me saying, how good did I measure 20 degrees here? Oh. Not even close to, you see how I'm like, you can't do this. This is the starting point. Okay, so we're gonna, what actual angle do I have measured here? About 30 degrees. Oh man, we did 30 already. And 30 degrees. Okay? And I got 8.5 over 17. Tan of 30 degrees, which I hope you see that 8.5 over 17 is about a half. When I do tan of 30, 0.57, pretty close to a half. Had my measurement been better, it would have been perfect. That's the power of your calculator and trigonometry. Okay, so questions for practice on this one. 3, 4, 5, 8, 9, 10. Now let's just do 12. 10.
Just giving up all questions.
We got everything. There's not very many examples in section 1, so. Now we got one more question to do in this section, so I'll only be able to give you 5 minutes to practice.